Okay, everyone, welcome back. Today we're going to start Chapter 6. We're looking at 6.1, which is an introduction to exponential and logarithmic functions, focusing on the graphs of these functions. So let's start off with exponential functions, and we've seen exponents before, but what we want to look at is the graph of something like y equals 2 to the x. With this type of function, you've got a base and an exponent. And unlike something like y equals x squared, it's the exponent that is the variable. In x squared, the base is our variable. We want to use a table of values to get a look at what this function will look like. So if x is equal to 0, for example, then 2 to the power of 0 is going to be equal to 1. If x is 1, 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, and so on. And we see what's happening is that this function is growing very rapidly. Each time x goes up by 1, y doubles. The pattern is backwards as well. Each time x goes down by 1, y halves. And we can use this to determine what's going on in our negative numbers. When x is -1, I would have 1/2, -2 for 1/4, and -3 for 1/8. We could go further, but this should give us a pretty good idea of what's going on here. So we're going through the point, let's see, let's give ourselves a scale here. 1, 2, 3, 1, 2, 3, 4, 5, 6, -1, -2, -3. So we've got the point 0, 1, 1, 2, 2, 4, 3, 8, and then -1, 1/2, 1/4, 1/8. And there is our graph. Now there's a couple things to notice with this graph. First of all, going to the left, it has a horizontal asymptote of y equals 0. Secondly, this function is always increasing. And as it goes to the right, it starts increasing faster. We could use this to talk about the end behavior, which would be as x goes to positive infinity, y goes to positive infinity, just like all of the polynomial functions that we looked at in previous chapters. However, the new thing here is that y is growing much faster than any function we've seen before. X squared grows pretty quick, but 2 to the x goes insanely fast. If I were to go up to 5, x squared would only be at 25, whereas 2 to the power of x, 2 to the 5th power is 32. And it goes even faster because every time x increases by 1, y is doubling. This is the fastest growing function that we are going to study in this class. Exponential growth is typically used to model different quantities that grow proportional to how much of that quantity there is. For example, population growth or investment in a bank account. We'll take a look at these later on in the chapter when we get to applications. For now, we're going to want to take a look at some basic properties of exponential graphs. These are all things that we saw from the previous graph. I just want to reiterate a few of them. The domain is all real numbers. Any real number can be an exponent. And the range is only positive numbers. There's no number you can put that will make our graph be 0 or be negative in y. The graph goes through the point 0, 1 and has a horizontal asymptote of y equals 0. The graph is 1 to 1, which you'll recall means invertible, and also continuous. No holes, no jumps, no vertical asymptotes. And the shape of the graph depends on the base. We've got two different possibilities here. If the base is between 0 and 1, that would be something like 1/2 to the x, where every time you increase x, y decreases, giving us a graph that's a mirror reflection of what we had before. In this case, it's growing as you move to the left rather than when you move to the right, and always decreasing instead of increasing. It has the same asymptote, it's just that the asymptote is on the other side. This is opposed to when b is larger than 1, which will give us a graph looking just like the one we looked at earlier, growing when you move to the right. Both of these graphs go through the point 0, 1, regardless of what the base is. Both of these points have the same horizontal asymptote and similar end behavior. The only difference is that the first graph is decreasing from the upper left, whereas the second graph is increasing towards the upper right. We want to use this idea to make a graph of this was supposed to be 90, let's fix that, to make the graph of a function that has been transformed. So we can use this equation to make a sketch of an exponential graph that has a lot of changes. Now, first thing I want to point out is this graph has the number e in it. The reason it has the number e scientifically is that e is an extraordinarily important number with exponents for a lot of reasons. And we're going to take a look at a few of those reasons coming in section 6.5 especially. But for now, we just want to know that e is just a special number like pi that's around 2.71. Meaning that this function, the basic function, y equals e to the x, is a regular exponential function going through the point 0, 1 and 1, e, where this would be about 2.7 or so. Then we'll just have to identify the transformations, and I see 4 transformations. I see a vertical shift, a vertical stretch, a horizontal flip, and a horizontal stretch. So again, we will first apply any stretching and flipping, and then we will do the shift upwards. So this point 1, e will be flipped and stretched horizontally and also stretched vertically. So if I were to apply just 90e to the negative 0.1t, ignoring the vertical shift for the moment, then we are going to go through the point 0, 90 and through the point negative 10, 90e. We can also sketch a point to the left of the graph. This would be the point negative 1, 1 over e, which means that over here, we would have the point 10, 90 over e. We can use our calculator once we've done our shifting to figure out roughly where that will be to scale. The last thing we need to do is apply the vertical shift. A shift upwards by 70 means we'll be going through the point 0, 160. And then through the point 10, 90 over e plus 160, plus 70, excuse me. We'll use our calculator to get a decent estimate of what this is. So if we plug this in, 90 over E, since E is about 2.7, we know this will be a little bit over 30. 90 divided by E comes out to be 33.1, which means when I add 70, we get about 103. We also can track where the asymptote would be. The asymptote of the original graph we know will be y equals 0, and that will be the same for the shifted and reflected graph. That won't change. Or, excuse me, for the flipped and stretched graph. But when we shift upwards, we'll have a new asymptote at y equals 70. We are omitting the portion of the graph in the negative x area, the quadrant 2, because for this graph, it's representing t minutes after it is served. So we don't care about the temperature of the coffee before it's served. This gives us a lot of information about what's going on here. When the coffee is served piping hot, it's at 160 degrees Fahrenheit. After about 10 minutes, the temperature has dropped from 160 to about 100. Eventually, if we leave the coffee sitting there for a very long time, the coffee will reach 70 degrees Fahrenheit. We can make the assumption, therefore, that the temperature of the room is 70 degrees Fahrenheit, and that this is the coolest that the coffee would ever get. Now, in this model, the coffee would never actually reach 70. After a very long time, it would be very close to 70, but it would not quite be there. Now, we talked about the fact that exponential functions are one-to-one, and that means that they are invertible. We're next going to take a look at what the inverse function looks like, and this is a logarithm. The inverse of the exponential function is called the logarithm base b, which is denoted with log base b of x. And the rule is that if y is equal to b to the x, this can also be written as x is equal to log base b of y. This allows us to isolate the exponent because what used to be the exponent is the isolated piece over here, whereas what used to be the isolated piece is now inside of the log. Log will be the inverse of exponent, and as such, all of its properties will be similar. Before we move on to graphs and properties of logarithms, let's just make sure that we have a basic idea of how they work and how we can find them. If it asks you to evaluate a logarithm, your best bet is going to be to convert to exponential form. So let's take this first one. What I like to do is I like to set a variable equal to the logarithm so that when I make the change, I have something to use as my exponent. Here, if I say y is equal to log base 2 of 8, then I can rewrite this as 2 to the power of y is equal to 8. This means that 2 to the power of 3 is equal to 8, as 2 times 2 is 4, times 2 again is 8, meaning that log base 2 of 8 is equal to 3. Thus, your best approach for these types of problems is to change the log into exponential form and then use your intuition. Of course, this is how we solve logs without a calculator. If you've got a calculator, you can, of course, plug it in, but we want to make sure that we understand what our calculator is doing, as always. Let's go through the next two. If I have log 6 of 1 over 36, we'll again set that equal to a variable. Doesn't matter what variable, I'm going to pick a different one just for the sake of example. Here we will have 6 to the power of w is equal to 136. Now I know 6 squared would be 36. Since this is a fraction, I know that I'm going to need a negative exponent because a negative exponent creates a fraction. So that will mean that 6 to the power of negative 2 is what we're looking for here, which means that log base 6 of 1/36 is equal to that negative 2. We'll do one more example here. Log base 4 of 8 will give us 4 to the power of w is equal to 8. Now, 4 is not going to directly get us to 8, but I notice that 4 is related to 2, and I know that 2 to the power of 3 is equal to 8. So I can rewrite this piece as 2 squared to the power of w is equal to 8, and then 2 to the 2w is equal to 8. Well, in that case, 2w would be equal to 3, so that tells us that w, since 2w is equal to 3, then w is 3/2. That means that log base 4 of 8 is going to be 3/2. Let's take a look at what logarithm looks like in a couple of special cases, because there are some logarithms that are used so frequently that we'll want a shorthand. The first one, called common logarithm, is a base of 10. The reason we like base 10 is because 10 is a very straightforward number. And logarithms are typically, just like exponents, used to talk about growth. When using a log base 10, it is easy to isolate numbers that feel very natural. So for example, powers of 10, 100, 1,000, 1 million, can be used to describe large quantities in ways that are very accessible. If I tell you that I have 1,000 people, for example, you know immediately that 1,000 people would be too many to fit in a classroom, but not enough to fill a football stadium. So that gives us a good sense of what that number is just by telling you that I have 1,000, which is a power of 10. For this reason, we like log power of 10 as well as exponents of power of 10, and we will write no base typically. If you have a log with no base, it is implied that the base is 10. The other special number that we'll like is e, and remember we talked earlier and mentioned that e is just a special number of about 2.7. 2.71 we'll say. Like pi, e is an irrational number. It is non-terminating the decimal. There is no fractional way to write it, and it goes on forever. E is going to end up being a very powerful number with exponents. You can remember E for exponents is a way to remember that E is a very important number exponentially. And because logs and exponents are inverses of each other, log base E is also very important. Therefore, we will call it the natural logarithm, and we will write it ln of x. ln, I believe, is simply natural logarithm in a different language. I think it's logarithm naturale. And so you can remember that the n stands for natural, and it is the natural logarithm, which is the log base of e. Now, logarithmic graphs, being the inverse of exponential graphs, are going to visually look like the reflection. We talked about two different types of exponential graphs. We had these where b is greater than 1. So this would be y equals b to the x. And then we had these where b is less than 1. Y equals b to the x. In either case, this will give us a sense of what the logarithmic graph will look like. It's going to be a mirror reflection, recall. So we'll be thinking about reflection across this line. And so we can get a sense of what the graph looks like. Over here, we will have something like this. And over here, something like this should work. Yes. And every property that we had with exponential graphs is simply reversed. So before, the domain was all real numbers and the range was positives. So here, the domain will end up being positives and the range will be all real numbers. The original graphs went through the point 0, 1 in both cases. Our graphs of logs will go through the points 1, 0. The original graphs had horizontal asymptotes. These graphs will have vertical asymptotes of the x-axis. The graph is still 1-to-1 because the exponential function is inverse, and it's still continuous. Similar to the exponential functions, these graphs are going to be growing or shrinking, but the difference is the rate at which it is growing. These are the slowest growing graphs. I'm going to write slow growth. These are the slowest growing graphs that we are going to look at. Think about the difference between x and y. In an exponential function, a small increase in x would make y grow enormously. So for a logarithmic function, an enormous change in x would indicate only a very small change in y. As a result, we get this extraordinarily slow growth in a logarithmic function. Now, we did a lot of practice of finding domains of functions, and we want to do a similar thing. We've now got this third restriction, which is that the log must be greater than 0 in terms of what's being plugged into it. So for this log here, x squared minus 1 is a denominator, and then I've also got the interior of the log that I have to worry about. So I'll have two restrictions. One is that x squared minus 1 must not be equal to 0. This quickly gives me that x is not equal to plus or minus 1. And then the second restriction is that x plus 2 over x squared minus 1 must be greater than 0. In order to solve this inequality, we will first solve the equation. And then create a number line involving the solution to the equation, as well as the places where the equation is not defined. And we will use some test values. Here, I like using a table of test values. I think it will end up making our task much simpler. So we'll have -3, -1.5, 0, and 2. And then we'll be looking at x plus 2. And I'm going to split up our denominator by factoring it, which I could have done in my solution over here. This would be x plus 1, x minus 1. So I'm going to include these factors, x plus 1, x minus 1, and then, of course, an equals area. So for these, this will end up being negative, negative, negative to make negative overall. The -1.5 will be positive here, and then negative. 0 ends up being positive twice, but negative for the third one, so negative overall. And 2 is simply positive everywhere. Thus, we can fill in the number line positive here and here, negative here, and here, yielding the result that we are looking for this region and this region. So that would be -2 to -1, 1 to infinity, the union of these two. Our domain will be these two intervals. We would need to double check, of course, that plus or -1 is not included, but of course, these numbers are where this piece is not defined, so they are not included as these places. They are the endpoints of the interval, so we don't have to worry about them. Finally, let's take a graph of an exponential function, sketch it using transformations, and then find and sketch the inverse. Now, we did an exponential sketch before. This time, there's only a couple of changes. I see a horizontal flip and a vertical shift. So like always, we'll begin with the original graph, y equals 3 to the x, which goes through 0, 1, and 1, 3. Not to scale, of course, but gives us a basic idea. A horizontal flip means that we will be flipped like this, going through still 0, 1, but now -1, 3. This would be y equals 3 to the negative x. And finally, we will apply the vertical shift, moving us upwards by 2. So we will have 0, 3, and -1, 4. If we want to sketch the inverse, all the x and y coordinates will be flipped. So we will go through 3, 0, and 4, -1. And it will look like this. The original graph had an asymptote at y equals 0, and the shifted graph has its asymptote at y equals 2, as we were shifted upwards by 2. Thus, the logarithmic graph would have its vertical asymptote at x equals 2. Everything is simply changed in x and y. That's all we've got for this lesson. We'll see you next time.